So hello and welcome to this video on the Hardy-Weinberg principle. This video is a part of our series on genetics, genetics made easy. If you haven't watched the previous videos, be sure to watch those. Now let us get into it. So in most of our calculation videos, we first start with the sample question and then I tell you how to solve it. So in a population in Hardy-Weinberg equilibrium, we'll talk about what this is. 9% of the individuals are born with an autosomal recessive disorder. So 9% have autosomal recessive disease. What is the frequency of carriers in this population? Frequency means how frequently this occurs in the population. Like what is the prevalence of carriers in this population essentially, right? So what is the percentage of carriers in this population? And then they give you this bunch of numbers, right? What do you need to do? Well, what's Hardy-Weinberg principle? If you remember your basic mathematics equation of a plus b whole square, that's a square plus b square plus 2ab, right? So what this guy Hardy came along and said, well, if a plus b square is equal to a square plus b square plus 2ab, then p plus q square is also equal to p square plus q square plus 2pq. And everyone was like, whoa. Well, that's not actually how things went. So what Hardy-Weinberg principle actually tells you is that assuming everyone's mating with everyone in the population, right? So there's completely random mating between the population and there's no natural selection. That means there isn't one type of gene that is dominating over the other kind of gene. There isn't one gene that is more suitable to survival than the other one. So no natural selection. If you don't know what's natural selection, be sure to watch my video on that. Right? So P in that case, in this equation, is the frequency of the dominant allele. P is the frequency of the dominant allele. Q is the frequency of the recessive allele. This is the frequency of the dominant allele, which is P. Q is the frequency of the recessive allele, which is Q. And then P plus Q is equal to 1. This is the Hardy-Weinberg principle, that if you add both the percentages, you will get 1. You'll get a total of 100% or just 1. 0.8 plus 0.2 is equal to 1, something like that. So that is the Hardy-Weinberg principle. So if P plus Q is equal to 1, that means P square plus Q square plus 2PQ is also going to be equal to 1 because 1 square is still 1, right? So what is the 2PQ in this case, right? What is the 2PQ? So let us take a look at this equation again and let's try to understand what this 2pq might be. So in this case, p square, what is if you put two p's, if the probability of having 1p and the probability of having 2p, this p square is the frequency of the dominant homozygous population. People who have two p's, 1p from the father, 1p from the mother. This is the frequency of having dominant homozygous allele for the p. And then q square is the frequency of having both recessive gene, Q from the mother and Q from the father. So what would 2pq be? 2pq is the frequency of being heterozygous. This is the frequency of being heterozygous, or the frequency of what is usually called carriers. Let's say if you're assuming that Q is an autosomal recessive disease, these are the carriers of this disease. These are the dominant gene does not allow the disease to express itself, but these are the people who are heterozygous and contain the carrier gene. So this is called carriers. These are the people who are homozygous for the carriers, and they are 2pq. This is the frequency of these heterozygous people. So if you draw the Punnett square for this, if you put p here, if you put q here, if you put p here, and if you put q here, these are the pp people, these are the qq people, these people are pq, and these people are pq. Therefore you have two pqs and one pp and one qq. So right here, and 2pq. So this is essentially Hardy-Weinberg principle. Now let us try to solve this question again. So we had this population in a Hardy-Weinberg equilibrium, right? And 9% of the individuals are born with the autosomal recessive disorder. What was our frequency of people having autosomal recessive disorder? That just means people who are homozygous for Q, that is Q square. So Q square in this case is turning out to be 9% or 0.09, right? 9% or 0.09 is the same thing. Okay, what is the frequency of the carriers in this population? So they want to know what's the frequency of carriers. So this would be 2pq. They want to know the 2pq. How do we calculate it? Well, we know that q square in this case is 0.09. So you put that under root and you get what? You get 0.3. What is the formula that will help us calculate the p in this case? Well, very simple. Just p plus q is equal to 1 will help us do that. What do we do? P plus q is equal to 1. So p plus 0.3 is equal to 1, and you put it on this side minus 0.3, and that gives you 0.7. So now you have 2pq is very easy to do because you have both p and q. So you do that, 2 into 0.3 into 0.7, and you have the value of 0.42. This is the frequency of carriers. This is the frequency of heterozygotes in this population. So these are the people, they said with autosomal recessive disorder, what is the frequency of the carriers in this population? This is the frequency of the carriers in this population. Now let's try to solve another question just for the practice sake, right? Let's solve another question. So in a population of 10,000 individuals, this is like the population. In Hardy-Weinberg equilibrium, 1 in 400 are born with homozygous, let's say they mean in homozygous for autosomal dominant disorder. So they're giving us what? They're giving us p square. So they're giving us p square, that is equal to 1 by 400. How many unaffected individuals are carriers of this mutant allele? So they want to know 2pq. This is what they want to know. And they're giving us a bunch of numbers, right? They're giving us a bunch of numbers. So how do we calculate? So we already have p square. So what we can do is that we can put it under root and let's see if we can get the value of p. So they have given us autosomal dominant homozygous. These are the homozygous for the autosomal dominant, right? And they want to know the carriers, which is this. So if you put p square is equal to 1 by 400, you put it under root, you get the value of 1 by 20. You get the value of 1 by 20. What do you do to calculate q? P plus q is equal to 1. You can use that equation, right? So 0.05 plus q is equal to 1, which gives you q is equal to 0.95. You can do this yourself if you want to, right? So then you put 2pq. Now this is very easy. So this will be 2 into 0.05 into 2 into 0.95, right? And that's exactly what it is. And then you calculate it. So this is 0.095. So this is remember, this is the frequency or the percentage. You can call this, this is 0.095. So you can call it 9.5%. Right? This is the frequency. So they want to know the number of individuals. That's why you will use the population in this case. So this was a population of 10,000 individuals. So 9.5% of 10,000 will be 0.095 or 9.5 by 100 is the same. You can use 9.5% multiplied by 10,000, right? So you multiply the 0.095 by 10,000 and you get the value of 950. These are the individuals who are heterozygous, who are carriers of this particular disease. So these are the people who are carriers of this particular disease. So let us try to solve this practice question together. So what you're going to do is that you can pause the video here, try to solve it yourself. If you can't, you can help solve it with me and you can understand what So let us try to solve a practice question together. What you can do is that you can pause the video here and try to solve it yourself. Okay, so let's do it together. So in this large population in Hardy-Weinberg equilibrium, that means they're mating at random and there's no natural selection. The frequency of the recessive allele Q, right? So the frequency of Q, they haven't given us Q square. They haven't given us the frequency of people who are homozygous for the autosomal recessive disease. They've only given us the frequency of the recessive allele. So they've only given us Q. Responsible for autosomal recessive disorders is 0.1. So Q is equal to 0.1. Out of 20,000 individuals, how many would you expect to be carriers? So they want to know the 2pq. They want to know the 2pq, right? So they want to know this value right here. So let us go into it directly. That we already know the value of q, which would be 0.1. We could just use p plus q, which would be p plus 0.1 is equal to 1. So if you minus this from 1, you get the value of 0.9, which would be p. So p is equal to 0.9. Now you can put them in the 2pq calculation to get the value of 2pq frequency, because they wanted the frequency of the carriers. Now let us put it in the formula, which will be 2 into PQ, which is 2 into 0.1 and 0.9. So this comes out to be 0.18 or 18%. So what you do is that you multiply this 18% with what? You multiply this 18% with the total population. Remember, this is the frequency or the percentage. This is not the number of people with the disease. This is the frequency or the percentage. And to get the number of, you always multiply the percentage with the actual number of the population, with the actual population, which in this case is 20,000 individuals, which comes out to be 3,600, right? And then let us go back to our question. So they have given us Q, and in a population of 20,000 individuals, we would expect the carriers heterozygotes of this disorder to be 3,600 people. This is the actual number of people with the disease. Now let us talk about a very specific phenomena called a rare disease phenomenon. What this means is that in some diseases, P plus Q is equal to 1, but the value of Q is so low. That means the recessive allele exists so low in the population that it's very, very small, that in fact P becomes roughly equal to 1. So now let us go into it. So in rare disease phenomena, what happens is that autosomal recessive diseases are extremely rare. Autosomal recessive diseases are extremely rare. That means the Q square is actually very, very small, is actually very, very, very small. It's way smaller than 1, right? Then P square actually becomes even bigger than Q square or 2PQ, right? 2PQ also is like heterozygotes. This means that the frequency of the autosomal recessive allele is very, very low. It's very, very small. In that case, you can just assume that P square or just P is equal to 1. This is the rare disease phenomenon, and this is all that you need to know about it. You don't need to know any more about it. And this is pretty much everything you need to know about the Hardy-Weinberg principle. You should know how to use the P plus Q is equal to 1 and the P plus Q square equations to solve these questions, to get the total number of heterozygotes or dominant disease carriers or the recessive allele carriers, all of that. That's all you need to know about the Hardy-Weinberg principle. What's the takeaway from this lecture? The Hardy-Weinberg equation is P plus Q is equal to 1, or P square plus Q square plus 2PQ is equal to 1. And what's the assumption? As there's a basic assumption that there is no natural selection, and the mating is at completely random, right? The mating is completely random, right? This is the basic assumption of Hardy-Weinberg equation. P square plus Q square plus 2PQ, which is, this is the frequency of the autosomal dominant homozygous carriers, homozygous P allele carriers. This is the frequency of the autosomal recessive homozygous Q carriers, and this is the frequency of heterozygotes. This is the frequency of the heterozygotes, right? And that's essentially all you need to know. Thank you so much for watching this video. Take the first step and the path will build itself. Thank you.